Hello, welcome to my virtual APS 2020 Mars meeting talk. My name is Joaquín Fernández Rossier, and this talk is about an itinerant fermion description of topological magnons in two-dimensional chromium iodine. This is theory work that we have done at the INL in Portugal, and Antonio Costa was the one who did the heavy lifting of this project. Let me give you some motivation. If you are in this virtual session, it's because you care about two-dimensional ferromagnets, and then you know that magnons are essential collective modes in this class of materials. Specifically, we care about chromium iodine, and here there is no consensus from the experimental side on what is the value of the anisotropy gap for spin waves in the gamma point, which controls magnetism in 2D. Neutron scattering experiments for bulk chromium iodine show that there is a gap in the Dirac points, and one important question is whether this gap is topological. And on the theory front, there is no consensus on what would be the effective spin model for chromium iodine. There are various anisotropy terms that have been proposed, like single ion, anisotropic stains, Delosensky-Morilla, Kira F, and so on. So the normal way to compute magnons is the following. You would start with a DFT calculation for the material. Actually, you would do many different DFT calculations to compute the various spin interactions. And that would give you a spin model Hamiltonian. And via the Holsten-Primakov boson mapping, you get a magnon Hamiltonian that gives you an energy dispersion for your magnons. The problems with this method are the following. First, if you want to derive n different spin interactions, you need to do n plus 1 DFT calculations with different magnetic ground states. And given that there are many different types of possible couplings, that makes n a very large number. And in addition, this method is not suitable for conducting magnets, but that's not relevant for chromium iodine. Here we take a completely different strategy, which is based on the itinerant fermion theory to compute magnons. Our starting point is a DFT calculation, only one, that gives us a mapping to a fermionic model, which is a multi-orbital Hubbard model, that we solve first in the mean field approximation, and then using the random phase approximation gives us the spin susceptibility tensor, whose poles are shown here in the energy and momentum space. You see here the poles, and that defines the energy dispersion for the magnons analogous to these ones here. Let me show you the details of this. So in the first step, we have this DFT calculation that I mentioned, and this is for spin unpolarized and ignoring spin-wave coupling. This permits to map a time-binding model for chromium and iodine atoms for the SPD orbitals of chromium and the sp orbitals of iodine. And here what you're looking at is a comparison of the DFT calculation and the time-binding, so you see perfect agreement. Now that we have our time-binding model, we add there the spin-wave coupling and the Hubbard interaction, multi-orbital Hubbard, and we do a mean field calculation. So the resulting energy bands are shown here for this method, and compare with that, not here, for this method, and we compare with the DFT calculation that includes both magnetism and spin-wave coupling. So you see a qualitative good agreement between these two. So the next step is to compute the spin susceptibility tensor, which is defined here as a retarded correlator for the atomic spin operators that are given in terms of the fermionic operators summing over the orbitals in a given atom. We are interested in the Fourier transform of this object in both frequency and momentum space. And the resultant of this procedure is a tensor which has the dimension of the number of magnetic atoms in the unit cell. In this case, 2 atoms per unit cell. So this is a 2 by 2 matrix. The poles of these 2x2 matrix are shown here in the energy and momentum space, and as I anticipated before, you see here the energy dispersion. And this is how this looks like now in a more conventional representation, energy versus momentum across the high symmetry lines of the breakdown zone for this honeycomb material. We have two bands as expected for having a honeycomb lattice, and there is the gamma point gap, which we get around 1 MeV, and there is this Dirac gap of 2 MeV. If we repeat the calculation switching off spin-wave coupling, we get here a Dirac cone, and down here in the gamma point we get no gap. Okay, so spin-wave coupling is both responsible of the Dirac gap and the anisotropy. This is how the Dirac gap, this one, depends on the spin-wave coupling of iodine, and we see that is basically pretty much controlled by this quantity. So now the question is whether this gap here is topological. So to answer this question, we have a look to the wave function of the magnons, which is defined like that. We take a given point in the momentum and energy plane, which is a pole for the spin susceptibility, and that defines this spin susceptibility tensor. And now we look for the largest eigenvalue eigenvector, and that's our spin wave or our magnon wave function. So the magnon wave function has both a weight on the A and B magnetic sublattice. Okay, so this looks pretty much like a wave function of a time binding model on a honeycomb lattice. Now we can compute the Berry curvature associated to this wave function, and we see how the Berry curvature peaks on both valleys k and k prime, and is positive in both of them. So presumably this will integrate to a integer Chern number. Additional evidence for the topological origin of the magnons in chromium iodine comes from the calculation of magnons in a ribbon. So here we repeat the same procedure, but now for a much larger unit cell, for a ribbon with armchair edges, and this permits to compute both the energy dispersion of these magnons, and there are now many branches, including these branches highlighted here in color that are inside the gap, the Dirac gap of the magnon dispersion. Now we can plot the amplitude of the wave functions associated to these bands as a function of position as we move from the edge inwards across the ribbon to the other side, right, for different values of momenta which are in this region here. And now you see how these two modes are decaying exponentially as you move from one edge to the other. So these in-gap modes are edge modes, and in this momentum region they are chiral, meaning that for a given side the dispersion is positive, for the other side is negative. So the take-home message of my talk is the following. Magnons can be computed without a spin model using the itinerant fermion theory, and we have very strong evidence that magnons in the chromium iodine monolayer are topological because of the existence of this gap Dirac point, the finite Berry curvature, and the existence of edge modes. With this, I thank you for your attention, and I also thank the funding agencies.